Okay, if you were absent from class today, we started a new section called Systems of Equations, which is section 9.1 in the Algebra 2 book. And what I did was I had passed out a worksheet. I can give you, if you're absent, you can get yours when you get back. We only really did one problem off of it, but we're saving the worksheet just to use for the whole unit. Okay, so the worksheet we started off with, we had two equations. And a system of equations just means we have more than one equation. It might have 3, 2, could have however many we want. We could call it a system of equations. And this first section, section 9.1 in Algebra 1, we're solving, there's like 4 different ways to solve these. But one way we can solve them is to solve by graphing. And so that's what we did today. So I'm going to graph the first line in a green color so that you can tell where it is. When we have systems and we try to solve by graphing, what we do is we graph both of the lines, and then wherever they cross, that's the solution. So you need really good graph paper to do this, or you get frustrated trying to figure out where that point is. If I graph that first line, y equal negative 3x plus 4, 4 is the y-intercept. I have a slope of negative 3, and remember that's a rise over a run, so I need a fraction. So I'm going to stick it over 1. So my rise is negative 3 and my run is 1. So I start at the point, the y-intercept, and I go down 3 to the right 1. And I'm going to go ahead and do several of these points just because I want a really accurate graph. I don't just want to slop a line on there. I want to make sure I'm very careful. So from that point, I'm also going to count off the slope. 1, 2, 3, 1. Down 3, right 1. Okay, so I'm going to connect that now. There was a stray dot there where I was counting. I don't want to go through that. I could go up 3 to the left 1 and get another point if I wanted to. Okay, so that's kind of sloppy, but I know where the solution is, so we're good. Okay, so now I got to graph the second line. The second line is y equal 3x minus 2. And the y-intercept there is negative 2, so I'm going to color it in. And the slope is 3. That's the slope. And remember, that's rise over run. So I need a fraction, so I'm going to stick it over 1 to make it a fraction. And I'm going to go rise 3, 1, 2, 3, run 1. Oh, look, I just found the solution because I landed on the dot that's on the other line. My solution is this point right here, which is the point 1, 1. When I find the point where they cross, that's the solution. And that's all I got to worry about. Now, not everything has a solution, and sometimes, okay, if the two lines cross, they've got one solution. 3 different things that can happen with systems of equations. I can have the lines cross in one place, so I'll draw a picture for that. And the solution is the point of intersection, the point where they cross. That gives me one solution. So that's one thing that can happen. Another thing that can happen is I can have 2 parallel lines. Let me draw in a different color the lines. Now we know if parallel lines, they never cross. So if they never cross, there's going to be no solutions because they're parallel. And then the other thing that can happen is I can have infinite solutions. And that happens, let's say I come along and I draw a line represented by that green line. And I come along and I graph the other line and it graphs right on top of the first line. Well, they were trying to trick me there. Those were really the same, both of them are the same line, aren't they? They just might look a little different. We're going to work an example here in a minute. If they're the same line, they're going to look exactly the same when what we usually do here is a lot of times when they give you problems like this, they disguise it by multiplying everything through by the same number and moving a bunch of terms around, okay? So in that case, if they graph to be the same line, every single point on the line both of them have in common. So we're really looking for what points the graphs have in common. So we would say there are infinite solutions because every single point on the line is in common with every other point. So sometimes I can actually solve these without graphing, even when I set out to solve them by graphing, because, like, for example, what if I had two equations? Usually I solve for y first so that I can graph them easily. So we end up putting them in this y equal mx plus b form before we go graph. And when I solve them, sometimes maybe I'd have something that looks like this: y equal 3x minus 1 and y equal 3x minus 7. Well, these two lines here have the same slope, so because they have the same slope, I know they're parallel already without graphing them, so I can go ahead and just say no solutions. I don't really have to graph them. If I see they have the same slope, I know they're parallel and they'll have the same solutions. The other thing that happens is, what if I had y equal 2x plus 2, and they gave me another equation, and they would probably complicate it more than this, but they might do something like multiply 3 by 3, and I might have 3y equals 6x plus 6. Well, if I solve for y, I'm going to find out I got exactly the same equation. They just multiplied it through by 3, and they're really good at hiding this by multiplying by maybe a fraction or some kind of weird number and then moving the terms around, okay? So this kind of thing can happen and not be as obvious as you might think it might be. So what we did in class, if you missed, worked some problems where we had those kind of weird things happen. Let's kind of do one of every type. If you notice on number 18, I'm going to skip first to number 18 in the book. You got a graph on 18 just to tell you how these things are going to work. And you got one parabola going like this, and you don't really have to graph any parabolas yourself in this lesson. It's all lines. You got another one doing something like this, and they ask you for the solutions. Well, the solutions are always where the points are that the graphs have in common. And so what that usually looks like is, where do they cross? So I would know these 2 points are the solution. Now, if you look in the book on page 18 and you look at where the points cross, they are at 1, -1, and 3, 3. So those are the 2 solutions on number 18. You would do 17 the same way. So we already did one where the lines crossed for our first example, the very first slide of the very first of this video. So what we're going to do now is we're going to look at some where we get infinite solutions or no solutions. So if you look at, I'm on chapter 9, section 1. I'm going to look in that very first section at problem number 7. I'm flipping to it right now as I... Okay, so we're supposed to solve this by graphing, but the thing about it is we may set out to graph it and not really need to find the answer. And in that case, you have my permission not to actually graph it to solve it, but just to go ahead and tell the answer. So I color-coded these because we're going to look at both of them. If I'm going to graph, let's say I plan on graphing in a minute because I don't know anything's going on with this thing. If I go to graph these, I'm going to want to solve for y first so I can graph easily. So that's what I'm going to do here. I'm going to start acting like I'm going to graph. I happen to have the answer key, so I know what's going to happen. I want to get y by itself, so I'm going to subtract the 3x from both sides. And I'm going to have negative 9y is equal to negative 3x. And I want to solve for y. Well, if I'm solving for y, I want to divide both sides by negative 9. And I get y equal, negative over negative is a positive. 3 goes into 3 once, and 3 goes into 9 3 times. So I get, this is my equation for my black equation that I wrote. Now I'm going to do the blue one. And you know what? I'm going to resist the urge to go ahead and graph these because I never know what might happen when I'm working these problems. So I go ahead, I'm going to go, okay, let's solve for y. Negative x plus 3y is negative 3. Here's the y. I'm going to move the x to the other side. That leaves me with 3y equal, I'm going to put the x first, so it's in y equal mx plus b form, x minus 3. And now to get y by itself, I need to divide everything by 3. Now if I go to look at the slope on this, because I kind of always want to compare the slopes before I actually go graph, just in case I could get by with doing a little less work, and we all seem to be, happy when we can get by with less work. If I want to know the slope there, usually the slope is the number in front of the x. Well, I have to kind of think about this x divided by 3 like this. There's an invisible 1 in front of the x. So this equation is really y equal 1/3 x minus 3. I want you to look at the slopes. This has a slope of 1/3, and this has a slope of 1/3, but these are definitely not the same line. One has a y-intercept of 0, and the other one has a y-intercept of -3. What I know about these lines is that they are parallel because they have the same slope. Since they're parallel, they're never going to cross, are they? Since they're never going to cross, they're not going to have any points in common, so there's going to be no solutions. Okay? So I can actually tell that this is not going to have any solutions because the lines are parallel and I didn't have to go graph them. So in that case, if you see that happen, you are welcome not to graph them because you can tell the answer without graphing. Now we're going to look at number 9. I'm going to do the same thing on number 9. Number 9 has the equations y equal 1/2 x plus 1. Yay, they already solved that one for y. I don't have to go do it. That's always reason to celebrate. And the second equation we get here is 4x minus 8y is -8. Well, if I want to solve for y, so I can put it in that same form so I can graph them easily in a minute, I could move the 4x to the other side by subtracting. I would have -8y is equal to -4x minus 8. And now I want to get y by itself. So I'm going to come in and I'm going to divide everything by -8. I'm going to get everybody their -8 instead of just drawing one line and putting -8. That way I can really see what's going on here. -8 divided by -8 is 1y, which is just y. A negative on the other side, if I'm looking in front of the x, a negative over negative is a positive. 4 goes into 4 one time, and 4 goes into 8 two times, so it's a positive 1/2 x. And then I look, -8 divided by -8 would be a positive 1. Well, looky there. These are exactly the same two equations. They just hit it by multiplying everything through by 8. If you look at the first equation we had, the second one is multiplied through by 8, and then they move some terms around to kind of disguise it. So we have two of the same lines. If I went to graph them, they graph right on top of each other. So they would have all kinds of points in common, wouldn't they? So I would just say there are infinite solutions, and the solutions are y equal, I have to tell, it's not any point on the coordinate grid, it's just the points on that line. So if I'm writing my solutions, I would say it's y equal 1/2 x plus 1. I would say infinite solutions. You would say that, and then you'd write this so people know that, yeah, they're the same line, and that's the line that they really are. That's all there is to this section. You have 1 through 11 odd, 17 and 18, and we just did 7, 9, and 18, so that doesn't leave you a lot to finish up. Hopefully you can do them.